Good morning. First of all, I would like to thank St. Joe's for giving me this opportunity to discuss on the work that we have been doing at IIT Madras related to high temperature materials. I also would like to thank my chairperson, Air Vice Marshal Umesh. Um we are working on high temperature materials which are produced by, we are trying to produce them by additive manufacturing. As Dr. Kamath mentioned a while ago, uh, the additive manufacturing is technology that we have to embrace it. There are a few talks, there is a separate session on additive manufacturing, but what I am going to discuss is whether can we print all the nickel based superalloys, high temperature alloys and all the alloys by additive manufacturing, and even if you print it, can we use them directly in the applications. So we have been doing the fundamental studies and characterization, testing, etc., to see those possibilities. So this work would not have been possible that without the help of many of my colleagues, Professor Murugayan, who is going to be present in the later, Professor Janakiraman in IIT Hyderabad, Dr. Kaundinya, who is as a postdoc, and other MTech students who have worked on this. And there is a quite a bit of generous funding that I have received from gas turbines establishment and Defense Industry Academy Center of Excellence. Formerly it was called as a COPT, Center of Propulsion Technology, Bombay. So this is something that you will see later about the additive manufacturing, but the simple definition is that the process of joining materials to make the parts from the 3D model data using usually layer upon the layer. There are various methods. There is a separate course by Muru, for example. There are 7 different methods. For the metal additive manufacturing, there are powder bed fusion, direct energy deposition, or the sheet metal lamination method. These are the ones which are used. LPBF, I mean, it's simply the laser powder bed fusion, is essentially uses the powder as the feedstock. So, and the laser as an energy source, and use the high purity argon atmosphere to maintain inside the chamber. And the advantage of LPBF is that you have a better dimensional accuracy and the surface finish. So that's the diagram that is shown on the right side, which shows that you have a powder bed here, and there is the building on which it happens. To talk about the additive manufacture of nickel based superalloys, so traditionally they have been produced using the casting or the forging various methods. So here I am going to discuss about 3 different alloys. One is Inconel 718, which is a precipitation hardened alloy. Inconel 625, which is a stationary system, it's a solid solution strengthened alloy. Other one is Inconel 939, which is used at slightly higher temperature, 850 degrees centigrade. So the question is that can we produce them by additive manufacturing route, and can we use them directly in these given the applications, or rather what are the traditional methods which are being used to produce these components, can the additive manufacturing replace it? In that process, I mean, if you see the what is advantage by additive manufacturing is that you can have any complex geometry, it can be manufactured by the AM. For example, the one which is the Agnilet, or also let us say earlier you have a rotor and the blades which are combined together. Instead, can we print the blisk entirely together? So coming to the LPB of nickel based superalloys, I am giving three examples which we have been working for the last 5 years on this. The first alloy is a solid solution strengthened alloy. The traditionally similar to like what we do the casting, right? So you we can use the component as it is after the casting. Similarly, in some of these additively manufactured alloys, you can additively manufacture it, print it, and directly use it. But at the same time, there are some alloys such as Inconel 718 or the 939. In those cases, I mean, you have to use the heat treatment. So I am going to discuss briefly on those 3 aspects of as built, what are the various parameters that we can control to get the required property, and what are the challenges. And if you take a precipitation hardenable alloy such as a Inconel 718, which usually undergoes quite a bit of the heat treatment. So I am going to touch upon whether the conventional heat treatment is okay to use it for this or not. And the third one is how we can change the various heat treatment methods and how we can get a different properties. So at the end, I will just summarize with challenges in name of superalloys. Yeah. So this is about the Inconel 625. It is among the many of the superalloys, it is easily printable because it is easy to weld. So the bottom line or the minimum requirement for something to be readily manufacturable or the printable is that it should be easily weldable. If it is easily weldable, then it is easy to print. But doesn't mean that something which is not weldable, it cannot be printed, but you just have to tweak other parameters to make sure that you can print it and then you can possibly use it. So why I have put this red here is that these are the elements actually which will dictate what kind of the challenges that you will see while you are printing them. And there will be more session about my in the additive manufacturing session about what are the various parameters that can be controlled. But the advantage of the LPBF is that there are various parameters that we can actually tweak it to control it. So here I am going to just briefly show it here scanning strategy. That means the layer by layer, actually I can go by unidirectional or bidirectional, or you can change it to the chessboard. That means within each square I can go bidirectional, unidirectional, stripe, and also 67 degrees rotation. All these things, different scanning strategies will give a different kinds of heat flow and different kind of the growth. So to give you an idea here, so I showed 3 different scanning strategies. The top one is the chessboard, and the stripe, and the remelted one. So what you can see is that as compared to the chessboard, stripe and the remelting has a certain amount of segregation, which is ideally not good for us. So though you have a finer melt pools in the remelting, but it is not sure that whether it is a right thing for our properties. Chessboard has a lower dendritic segregation. So here I am going to give the properties of the room temperature and the high temperature. They are done at the constant the strain rate of 10 to the power of -3 per second. What you can see is that just because we have changed the scanning strategy, we see a difference in the properties where the chessboard gives me almost like the higher elongation as compared to other 2 scanning strategies. Similarly, if you look at the in terms of the high temperature strength, so here the chessboard is slightly lower, but it has a better ductility. So similarly, some of these components have to be qualified for their creep resistance. It means that they have to withstand a time dependent plastic deformation that undergoes at the high temperatures. So we have to do the testing as well, some of these for these materials. We have done the creep testing in our lab. What you can see here is that all these, the red, the black symbols, the black spheres, that is for the chessboard, that gives a better creep rupture life. So though you have a higher strength in some of the other scanning strategies, the one which is giving the better creep rupture life is the one with the chessboard scanning strategy. So just to summarize the work on Inconel 625, so chessboard strategy gives a less segregation, so which is better. Probably it is giving a better creep rupture life because of less segregation. And what we have been working on, it is a part of the MTech project. So the multiple boundaries acting probably as a crack initiation sites for the creep deformation. Let me go to the Inconel 718. This has been at least most of the metal additive manufacturing actually has started with Inconel 718, including the Agnicol has been doing a lot of work on Inconel 718, but there are challenges remain. So for example, here what you can see is that I am showing along the build direction and the normal to the build direction. If you see, the microstructure looks very different, right? So in the case of the normal to the build direction, you have the laser tracks which are actually coming from the melting, and here what you can see along the build direction you have the melt pools. And if you go a little deeper into the microstructure, you have a columnar and the cellular dendritic phases. So now the purpose is we need to find out whether we can get a better properties. So here what I am showing is that, so I have done the vertical build as well as the horizontal build. Now I have tested them on the vertical build samples as well as the horizontal build samples, because ideally I would like to see if I print it by vertical or the horizontal or the 45-degree angle, I should get the similar properties. So if you look at here, the one which is built by the vertical build, it shows a higher elongation, but the horizontal build one actually gives the higher strength. So with horizontal one, you are not getting the elongation. So both at high temperature as well as room temperature. So possibly because of you have a higher number of the grains along the horizontal direction, that's why you get a better strength. But if you look at in terms of its creep properties, the horizontal build and the vertical build, so what you see here is that the horizontal build doesn't give the better creep rupture life. In fact, the creep ductility is very low. So that you can see from the plots here on the strain rate versus the strain here. So where the horizontal build one fails within the less than 1%, but the vertical build one has a slightly better rupture life of almost like 326 hours, and it has also the lower the creep rate, which means that it's a better creep resistance. So we are trying to understand how you can have a anisotropy in both are the horizontal and the vertical build, and by choosing the heat treatment or by changing the scanning strategies. Yeah, so these are the fractographs usually that as a metallurgist we go through it, and now you can see that why the horizontal build one actually they failed at a much the lower the creep rate, the higher creep rate, and at the lower creep rupture life because of the brittle mode of the failure, and possibly because of more number of grain boundaries and more amount of segregation. Yeah, so to summarize this part, the VB specimen so far seems to be good, and the premature failure in horizontal build attributed to a kind of a chemical segregation. And what it means is that unless we employ a certain amount of the heat treatment, it's not easy to actually to get the properties what we are looking for with additively manufactured one. The last one, this alloy is a slightly the high performance alloy, which is used at high temperatures around 850 degrees centigrade. This is for example used in the vanes, the guided inlet vanes, and here because of the titanium, aluminum, the tantalum which are in slightly higher amount, its weldability is little challenging. So here the graph what it shows is on the y-axis the nickel and the tantalum and the aluminum, on the weight percent of aluminum on the x-axis. So anything above this 45 degrees the line, above that is very difficult to weld. It means that it is very difficult to additively manufacture. Below that line are easily weldable. Because of the kind of the strengthening that we get, which will give its a high temperature the properties, the same properties are actually responsible for the lack of easily weldability of or easily manufacturability of this particular alloy. But it has to be, we have to deal with it. So typically what we do is that we choose the various the laser the parameters or additive manufacturing parameters of the layer thickness, hatch spacing, and laser power with all of together, and we have optimized it, and we have produced the one which you shows the S8 gives the better microstructure as compared to all other the parameters. So now what we have done is that we have taken that and we have done the heat treatment at 4 different kinds of the heat treatment given. This alloy has not been published pretty much in the literature yet. So the challenge is to what kind of heat treatment will work. Okay, so whatever the conventionally given the heat treatment, whether does it work, our understanding right now is that it doesn't work. So we have given the 4 different heat treatments. 4 different heat treatments gives a 4 different kinds of the properties. In other words, for example, here if you see the one which is the HT1 gives very high strength, but it is a lower ductility. Among this, HT2 seems to be giving the better one. And more importantly, we try to tackle what that kind of anisotropy with the horizontal build, the vertical build. So what this plot shows is that here both at the room temperature, at high temperature 850 degrees centigrade, 950 degrees centigrade, if you see the heat treatment 2 and heat treatment 3, the anisotropy is much lower. So it means that the conventional heat treatment doesn't seem to be working. So in the last slide of the talk and about the challenges in the additive manufacturing of high temperature nickel based superalloys, we have to understand that not all the superalloys are easily additively manufacturable. So we have to tweak the parameters to print them. Conventional heat treatment, what is traditionally used for the cast or the wrought products, may not necessarily best for the additively manufactured nickel based superalloys. And there is a orientation dependence or the build orientation dependence of their properties, both in the high temperature properties and the creep properties, that needs to be studied. And role of columnar grains with different aspect ratios for high temperature deformation needs a much more the research. So these are the equipment that we have developed in the last 10 years to do this research. The bottom one shows the iFusion SF1 which we have procured from Intech Additive. Others are creep frames. We have the lab to conduct the high temperature testing up to 6 months or 1 year. We have close to 10 creep frames of different capacity. We have also built few creep frames our academic the purpose. Yeah. Thank you very much.